I hope some of those direct methods have been of interest to you, and you would have seen, hopefully I've added some interpretation to them, but I know there are some AI skeptics out there who might view these methods as just discarding physics and picking up a book on kind of, if you like, mindless nonlinear algebra, just do anything, just stir the pile of parameters and hope. Now some of them can seem that way, although I hope I've motivated what's going on so that it doesn't seem as bad as that graphic implies. That graphic, by the way, is taken from that paper there that I've just recently published with Gail Schramm. But what I'm hoping to convince you of next, I've only got about 25 minutes left, is to say that actually the best thing to do is to kind of do both. You want to get your AI stuff, and then you also want to get your physics embedded in there as well. So if you're an AI disciple, so to speak, and a reconstruction expert, then hopefully this is the picture you will be looking at, where you want to blend these two together, the inverse of the radon transform, as well as AI learning for the bits that we don't know. Okay, so I've got 25 minutes, that's good. Okay, to catch up on now the important final stage I want to go through, which is deep learned iterative image reconstruction. So to review where we are with direct AI methods, the benefit is they've got very few modeling assumptions. You just effectively have what we call the inductive prior of the architecture. And obviously a certain architecture is only going to be able to express certain images. Well, it depends on the complexity, it depends how you designed it, and that's effectively the model that's being used. But other than that, there's no physics model, there's no assumption on the stats and so on. Obviously operates on raw data. Inference, once you've trained it, is very fast. Put a sinogram in, boom, there's your image. However, they're going to be slow to train, huge training data needs, many training pairs required. And also ignores our knowledge of the imaging physics, ignores our Poisson noise model, huge network as mentioned, mainly demonstrated for 2D reconstruction, and then you've got this question of generalization. If you're doing some kind of XY linear regression, for example, as long as you're sampling in your domain of interest adequately in your training data, then you're okay. But of course, unseen data, you don't know what's in the field of view. Are these methods going to give you a result that is fully trustworthy? In other words, generalization needs to be considered. So now then, with these unrolled iterative methods I'm going to get on to next, we're going to be taking some of the benefits of the deep learning, CNNs, AI, and combine them now with our imaging physics system matrix and our Poisson noise model, use the raw data directly, keep the machine learning paradigm of fitting to high quality references rather than fitting to noisy data. And then these are going to prove to be practical for 3D reconstruction, and they'll have far lower demands on training data. Typically, only tens of examples are actually required to train up relatively reduced numbers of parameters. There are many ways of doing this, and Jinyu will be touching on alternatives in his part of this course. He'll be talking about how you can use a CNN model for the image, just like you use kernel model for kernel EM. You could use a CNN as a penalty for a regular map reconstruction. But the focus I want to put here is using a CNN for the regularization prior within a map EM reconstruction, iterative reconstruction. And the benefit here is that when we train up that CNN, as all part of the process, there would be implicit knowledge of the physics model that we're using at the same time. So that's potentially a benefit. Rapid then overview of reconstruction. There's the well-known Poisson log likelihood. I really don't have time to dwell on this for too long. There's the Poisson log likelihood. What we're trying to do is find an image X, which when you forward model it, best agrees with the measured data. So we're talking about the likelihood of an image vector X given a measured sinogram M. And this is just derived from a product of Poisson distributions. So once we've got that Poisson log likelihood objective function, so for MR this would just be a least squares objective function. For PET it's obviously this one here for the Poisson noise model. As we know, and in fact this applies for gradient descent, for even for training neural networks, what you do with gradient descent, or here gradient ascent, is that you find the gradient with respect to your parameters. And so for this objective function here, if you've got a given image xk, then you can find the gradient image, and then what you do is add on the gradient to get you closer to the maximum likelihood solution. So this is very well-known stuff. This is just the well-known MLEM algorithm that takes you from a current image estimate and gets you closer towards the maximum likelihood estimate. Just like what you'd be doing with the gradient descent methods for improving your learned parameters of your architecture. There'd be a similar gradient descent going on there with Adam, stochastic gradient descent, and so on for least squares context. Okay, the point is that well-known MLEM algorithm, which we all know is take an image, forward project it, take the ratio of the measured data, back project it, multiply to get the update, normalizing by the sensitivity image. That well-known algorithm can just be unrolled and viewed as a cascade of operators. So these are like layers in a network. We've got the initial input image, we do an EM update, we've got another image. So these could be those well-known rectangle representations that we've seen in deep architectures. And so we can just view that EM algorithm as a deep network where each of those updates involves those very simple processes. And just to point out, it was Gregor and Jan LeCun, one of the so-called godfathers of deep learning, that was actually on this very early paper on unrolling iterative reconstruction, and they had, I think it was learned ISTA, iterative soft thresholding algorithm. So this goes back, this concept, many, many years, and you could argue in the image reconstruction, medical imaging community, we've been pretty slow to pick this up, given that came out in 2010. Okay, so the point being, remember those early slides, what we're trying to do in machine learning is deal with the fact we've got noisy data, and we need to compensate for that. So if we had high quality data, we might get a high quality image there, but if we're just doing MLEM, we can end up with noisy reconstructions from noisy sinograms. So what do we do conventionally? Well, conventionally we would do a penalty as implied in those early slides. So here now is this is the Poisson log likelihood that we're trying to find an X that will maximize that. But now with that penalty, and I'm using U here rather than R before, as my penalty. So this is actually the log posterior, in which case that would be e to the minus beta u of x, but by taking the log it just becomes this simple subtraction. And we could use, for example, a quadratic penalty like this. Simple as that looks, this is actually quite a difficult optimization problem, but De Piero came to the rescue as follows, just to talk you through what we're doing first of all here. To maximize this objective function, if we just had the Poisson log likelihood, then we'd use the EM update, which is basically maximizing a surrogate function. Okay, the surrogate function will be the complete data Poisson log likelihood, and we can get to the maximum of that in one go using the EM update. But of course that's based on an estimate of the complete data, the conditional expectation of the complete data given measured data and an estimate xk. So this well-known EM update will step us towards the maximum of that part there. And then also there was a surrogate method proposed effectively by De Piero to deal with that problematic function here, where this intermediate image is going to be basically minimizing a surrogate objective function for the u of x. So this is going to get us closer to where we need to be in terms of reducing u, and this is going to be getting closer to where we need to be in terms of maximizing that. And the well-known MAPEM method, and Jinyi will be using this later on in his presentation, you end up with this kind of formulation here where you can say the next update is given by the EM update in combination with effectively a denoised or smoothed version of your current update. So this is a really simple process. You can view it as an initial image going into a MAPEM update. Notice I'm unrolling it again as a cascade of operators here. So we'd take the image, we would denoise it to get X smoothed, we'd do the data-based update to get XEM, and then we'd fuse those two together using this well-known update. This even tracks back to Levitt and Herman way back in the 80s. You could look at their original work where they had a prior image. It was De Piero that allowed us to do this neighborhood-based approach here. But anyway, just to view it therefore as this cascade with this denoising and this EM update operator. So that's conventional, and you'd end up with a quadratically regularized reconstruction instead of the noisy one we saw before. We did go a bit further, as you know, by using anatomically guided methods. Sorry, just to mention, this is obviously not necessarily going to be optimal because we don't know that quadratic is the best penalty for our reconstruction problem, so it's not likely to be the best. But anyway, we did upgrade this in conventional state-of-the-art reconstruction by, for example, building in MR information such as via the Bowsher method, where you end up with a binary set of weights to basically give you an MR guided smoothed image here, which you then use in this position here instead of just the unguided one in the previous example. But the question here would be how much MR guidance to use, and as pointed out, even for this quadratic prior, that's mathematically convenient, even though that was a challenging problem originally, mathematically convenient, and it's not likely to be optimal. And so this is where deep learning can come in and actually learn what it is that actually we don't know if we're really asked. I think we're fairly confident with the Poisson noise model and our imaging physics, but when it comes to what prior and penalty to use, it's a bit of a claim to say that quadratic prior will do the job. So let's take this unrolled MAP-EM reconstruction. This will obviously go on for many, many updates, perhaps 60, whatever is your normal number of iterations. And in fact, to point out there, you could argue we're no longer necessarily converging to a map estimate if we use a limited number of iterations. But there are some really nice techniques out there, like deep equilibrium that's coming out, that can really generalize these methods even further. Anyway, just to stick with this finite number of iterations for the moment, what I'm showing here is how we can now embed a CNN or some deep learned deep noiser into that MAP-EM framework. So we've got an initial image coming into these modules, and each module looks like this, where what you do is you take your image, you denoise it. That's like getting that intermediate image that we saw that was going to arise from that surrogate objective function. So this is basically denoising that, and then we use that denoised image as a point-by-point prior to penalize our EM update. So that's that MAP-EM fusion update that I've just shown you, which just basically uses these in combination to deliver the next update. And what we're going to do in deep learning, of course, is use high quality reference data. So again, that could be found by simulation or found by high stats acquisition, whatever it might be, where you don't need regularization, or if you do, you make sure you know exactly what you're doing to make sure that you've got something very desirable here. So something very desirable would be high count data, reconstruct it, there's our reference. And then the point is, here now with noisy data, we're going to end up with some noisy result. Here I've already put the MR guided one in, so it looks pretty good actually, so that's a bit misleading. But in general, that's going to be a noisy outcome, although you could argue if I've now trained up my deep denoiser, my result might look like that. This is just an illustration. I'll show you real results in a moment. What we're going to be doing is simply defining a loss function that says, well, when I run this through my unrolled network, I get a reconstructed image here, and I need to compare that to my high quality target using a mean square error loss. Now in these methods I'm about to present, they are mean square error loss using methods, but of course we've seen earlier with DPIR-Net, you could have a discriminator, you could have perceptual loss, you could upgrade this as you may desire. And also later on, if I've got time, just to point out that just like that principled method where we broke down the direct reconstruction into different segments, you could kind of do the same here and start putting loss functions midway as well and impose requirements as you cascade, as you go deeper into the network. But the point being, just think of input data in, output here, get it to agree with high quality reference, and what we'd be doing is taking the gradient of that loss function, back propagating to update, again using Adam, stochastic gradient descent, whatever you prefer, to update the parameters that are in this denoiser here. Now this denoiser could be unique for each module, or it could be the same, and that's where we've got different methodologies. And in fact, I'll move on to this table here, where indeed I point out that, for example, Gong's method, MAP-EM-Net, which basically follows that overall structure I just showed you, he used a different network for each module, use mean square error, and also notice on this slide we're now dealing with 3D images and relatively low numbers of training data pairs. Okay, FBSEM-Net I'm going to show you more of in a moment. We use the same architecture for all iterations and modules, and then BCD-Net, or in fact it was published as iterative neural network in TMI in 2020. also had iteration-dependent modules. And of course, the more modules you have, therefore, the more parameters you end up with. And then also to point out, Guillaume Corda-Dancon has just published recently a sequential training version of FBSEM-Net. I might show you some examples of that if I've got time. So looking at FBSEM-Net, this is typically what's going on, giving you some more of the architecture details. This is the denoising block. This is the EM update. We've got some image estimate XN going into both, fusing together with the map-EM update to go into the next block until we get some endpoint. So what's going on here? Well, we've got the well-known log posterior objective function here. In other words, it's a Poisson log likelihood with a penalty term, and we're trying to find the X that maximizes that. Given a current XN, what we can do now is learn that prior image. Now, I refer you to what I talked about before with the de Piero method about using a surrogate objective function and so on. So you could view this as a gradient descent on this function u of x. But what we're going to rather cheekily do is say, well, okay, we're just going to use a network to do the entirety of that process. We're not going to make any claims about what the gradient of that penalty should be. We don't even know what the penalty should be. Let's just learn whatever it is we need to learn that will best capture what that should have been in order to get our high quality outputs. And then we do basically, effectively, we've got a, what's called this proximity operator. It's just a penalized update that we've been dealing with all along. So we're just trying to maximize the Poisson log likelihood here, but subject to the X shouldn't be too far away from that smoothed update, that intermediate image, that deep learned denoised update. So, so you'll come across this construct later on as well in Jinyi's part of the course, where he'll be talking about alternating direction method of multipliers, and this is very similar to that, except that we don't have the Lagrange multiplier in here, whereas in the methods he's presenting there will be an extra term in there. So this is based on the forward-backward splitting method, for which you can find references quite easily. Anyway, what we do then is we're trying to get this update here, maximizing the Poisson log likelihood, but making sure it doesn't drift too far from our denoised image. And so we can do that using the well-known methods. Of course, the EM update takes care of increasing this, doesn't maximize that, but it will maximize the surrogate function. And then we've got the well-known map-EM update to account for this requirement that we shouldn't be too far from our smoothed update, our deep learned denoised update. So this again is just another rewriting of that well-known fusion block, joining together the data-based update with the deep learned denoised update. So a quick look at the results here. This is for simulated data. Huge number of counts in the high quality reference here. Conventional reconstructions, OSEM, using 100 times fewer counts. No surprise, noise is showing up. And then when we do MR guided map-EM, we get a result like this. And then deep learned methods are shown on the two rightmost columns here. This is FBSEM-Net that I've just described to you. And a little bit disturbing here in this case, maybe not the best way of selling the method. Just showing here a conventional UNet that's being trained up, and it's actually doing a very good job here as well as FBSEM-Net. For real FDG data, this is from the MMR scanner. Again, we've got the high quality reference. So we're using higher, longer acquisition time now for the high quality reference data. And then we've got reconstructions, conventional OSEM here, suffering from noise as expected. The deep learned methods using MR, so that's an unfair advantage compared to this one here, but training up those deep learned denoisers in FBSEM-Net. In fact, there's only one that's repeated for all modules for FBSEM-Net. You can see that it's delivered notably improved image quality compared to OSEM. And again, the conventional post-reconstruction UNet doing surprisingly well also. So just to touch again on that idea of putting the mean square error loss at every single iterative update, and that kind of controls the process, because what can happen with deep networks is if you just train end to end, you kind of don't necessarily know what's going on midway. And so one workaround for that, I mean, in fact, what can happen is a lot of the work can be done right at the end of the network. It just does all the fixes for all the stuff that it didn't do early on in the deep cascade of operators. So this iteration-dependent, module-dependent network version of FBSEM-Net basically inserts not just the mean square error loss at the last module, so this is the high-quality reference at the bottom, this is operating on the noisy data here. If you just reconstructed the noisy data with no special measures, you'd get this. Running it through the network, you get this. This is the high-quality data. So instead of just doing the mean square error there, oops, okay, am I back? There we go. We also now do it at every single update. Okay, and that's controlling the process to say even after the first update, make sure you match the high-quality reference and learn a network that will do that job. And so he's shown some quite nice results. This was published earlier on this year, and he compared it with BCDNet and the iterative neural network, rather, I should say. And really, I mean, you're maybe hard-pressed to spot major differences in the images here. The main gain he's got here is also training those modules sequentially. Instead of having to back-propagate through the whole network to train up all of those modules, which is what you should do properly, by doing a shortcut of sequential training, which I believe is also what was effectively done in the iterative neural network method, Lim et al. As the reference given there. That gives you a massive efficiency gain in terms of memory, which means you can actually train up every single module for something like MLEM with no ordered subsets or whatever. You can actually do every single module and train it up in a practical way. So maybe that's the selling point for that method. Okay, I think I'm doing okay. I've got 4 minutes left. I can't advance my slide now for some reason. Okay, don't know why that's not working. It's locked on the laser pointer. Okay, right, and also showing these methods in terms of bias standard deviation trade-off. This is showing a low count OSEM, and so as expected, standard deviation goes up with reducing bias. The high count reference is shown here, and in an ideal world, our deep learned methods, of course, would take stuff from here that would have been reconstructed there and put it on that line there. And you can see we're not actually achieving that. We're kind of halfway between the two, but I don't think we can complain. This is already a significant upgrade compared to where we would have been. And then this is zooming in on that melee of graphs here where we're comparing FBSEM-Net with the iteration-dependent version, which is shown on that line there, and it behaves in a similar way effectively to the iterative neural network example. So it's showing that there are some small advantages, but I think the main one again is training practicality. Okay, my last 3 minutes I think that I've got, I can just touch on some of the research areas that we're developing on this topic, and there'll be a presentation on this in the reconstruction session. What you can do is what I've been talking about is unroll MAP-EM, and this FBSEM-Net like I'm showing there. You can do exactly the same kind of stuff for MR, and there's been a lot of work, Hammer-Nick et al. Have done some beautiful work on unrolled MR reconstruction, learning the potential functions and so on. So normally you could do this independently to reconstruct your PET data and your MR data, but of course with deep learning, the sky's the limit really, and you can start to benefit from the reconstruction of each modality to try and assist the reconstruction of a given modality. So here the PET is also taking feature maps in its regularizer, in its deep learned denoiser, is taking feature maps as inputs from the MR reconstruction and vice versa. So that's with a view to trying to attain some kind of synergistic reconstruction. And there's a lot that could be said on this, but I'd point you to the presentation later on in the conference. So to summarize on my part, hopefully these are the take-home messages that you've been picking up. Conventional image reconstruction is nice, but it's only based on a model. It completely ignores knowledge of high-quality data or a ground truth reference. And so you end up fitting parameters to noisy data. And then conventional strategies for mitigating noise are often too simplified. I mean, a quadratic prior, it's pretty basic at the end of the day. And then not only is the prior often too simplified, Also, you need to choose the magical strength of regularization, the hyperparameter, and these are ongoing topics of research. In contrast, machine learning uses a high quality reference, and it maps your noisy data through a cascade of operators to your high quality reference in your training set, with the idea being that when you've got new unseen data, you can rely on those same trained networks to deliver a high quality output. I've touched on direct AI methods. I've given quite a few examples to you, but they've got huge training needs. They don't build in the physics, and they're often mainly shown for 2D cases, and maybe generalization is a query. Physics-informed methods keep on visiting the data at every single iterative update, and they build deep learning in as the regularizer, and they therefore have reduced needs of training data. They've been shown to be good for 3D data, and okay, we need to show this increasingly in research, but are arguably going to be more reliable and more generalizable. Future directions, well, I've just touched on synergistic deep learning, just showing you an example of where we could go with that. That is still work in progress, I have to say. When you see that presentation, it's not like we've arrived by a long way yet. Architectural design choices, the inductive prior that you're using, a lot that could be done there. CNNs. I haven't had a chance to even talk about transformer networks. They're very exciting. Also modeling of uncertainty, and then modeling that, we could then build that in and use it as well. And also the training data. Obviously, that's always going to be a major issue here. And there are all kinds of methods out there in the deep learning world that are really into unsupervised pre-training, through pretext tasks and so on. So there's a lot of work going on in deep learning that we could yet make use of in medical image reconstruction. And as with all methods, clinical assessment is always going to be needed for a real task-based evaluation of how well these methods are doing, how trustworthy they are, how reliable they are. So I think that's basically my part done. I just want to acknowledge the co-authors on my recent deep learning review article. So Guillaume Corda, Abba Fazmarinian, Casper da Costa Lewis, Sam Ellis, and Julia Schnabel. And there's that review article. That's quite old now, that review article. It came out properly in 2021, but it really is from last year. So I'd probably write that article differently now, but there you go. Hopefully of use to you. And then a more recent kind of perspective that was published in JNM. So just point you to that as well if you want more information.